So when I started my journey with Kubernetes, I was wondering how everything works under the hood, how the small pieces connected with each other became one of the most advanced distributed systems in open source world. Today, I'll be talking about Kubernetes cluster Bootstrap in general, without focusing on any particular cloud provider or virtualization environment. Hopefully, it will give you an overview how various components fit and work together, and obviously how the provisioning process looks like. Few words about me. My name is Bartek Antoniak. I work for Virtus Lab as platform engineer, DevOps, name it as you want, on custom Kubernetes distribution in cloud. On top of that, we try to build deployment platform. Also, I'm a huge fan of Golang and security. You can find me on Twitter if you want to. Well, I would like to start with following slide, which shows what me and my teammates have managed to do in order to better understand provisioning process from slightly different perspective than usual, because we spent most of the time with cloud, so we wanted to learn how it works all the way down to bare metal. So this is Franken-cluster. It has 3 Intel boxes with x86 CPU architecture, which means that we can run almost everything there. It's not ARM. It has network switch, Raspberry Pi, which works as provisioner for other nodes, and some 3D printed stuff to combine everything together. Obviously, there are some limitations and we have future goals. The first one is to make it portable, to show you how it works, because it requires router. Also, I would like to investigate remote power on and off using IMP tool, and some better Docker images for Raspberry Pi, which is obviously ARM architecture, and some of them doesn't work out of the box, and probably any more. So any ideas highly appreciated. How many of you are familiar with Kubernetes? Raise your hand. Oh, that's nice. So just briefly, so Kubernetes is a platform which runs and manages containers. It has declarative configuration and automation like service discovery, health checks, auto-scaling, and many more built in. It supports multiple container runtimes, and it's 100% open source, written in Golang. This is very well organized open source project, probably the biggest one in the open source community. So you need something like Kubernetes in order to make containers practical. Let's be honest, containers itself are not so useful without proper abstraction and automation layer. It will be really hard to run complex distributed system just on Docker. But what actually is a Docker container? Many people are confused. There is something more than operating system and physical infrastructure. But the thing is that it's just a process isolated using some kernel features. So it has own process space. It has own network namespace. So everything is isolated on the network layer, and it has own network interfaces, routing tables. Also, it has resource limits based on C groups, and security stuff like SLLinux, AppArmor to limit access to specific syscalls from kernel. Before we start digging into the actual Bootstrap process, let's take a look at the Kubernetes components in order to understand what we are going to provision. So as you can see in this example, we have 2 workers and 1 master node. API component is running on master node, and it exposes Kubernetes API for every authenticated and authorized user or service in order to create Kubernetes objects, which are stored in SHRD, which is key value data store. Controller takes care of managing cluster state based on Kubernetes objects stored in SHRD. Kubelet is a primary node agent, and it manages containers, but note that it doesn't manage containers which were not created on Kubernetes. Proxy is just TCP and UDP forwarding for Kubernetes services. And pod is just a group of containers running on the same node with common lifecycle. Under the Kubernetes abstraction layer, there is nothing more than operating system with configuration, some networking stuff like virtual interfaces, IP tables, rules. On top of that, we have systemd services and container runtime. Containers communicate with each other using CNI, which stands for Container Network Interface. Pavel will give you more insights about that, but it's mostly based on virtual interfaces and IP tables magic. In some cases, there might be virtualization underneath, for example, in the cloud. Just briefly about SHRD. Like I said, it's distributed key value store. It has state for entire Kubernetes cluster. It runs gRPC service over TLS, and it uses Raft consensus algorithm to agree on consistent writes and reads. Okay, let's move on to the Bootstrap process. In order to understand Bootstrap process from very beginning, let's start with bare metal example. It involves number of technologies like PXE enabled network boot, DHCP for network configuration, TFTP to transfer data, OS image, it will be container Linux for CoreOS in our use case, OS configuration, it will be Ignition with systemd services. I will be talking about Ignition in next slides, and obviously Docker. So one of the key requirements for provisioning is the server ability to boot over the network, and PXE is the one of the ways to boot over the network, and PXE server is nothing more than DHCP and TFTP servers. It provides kernel image and root file system. When PXE client starts, network interface card sends DHCP broadcast request, and DHCP server responds with network configuration like IP address, netmask gateway, DNS. In addition, it provides location of TFTP server. Then clients connect to TFTP server and gets boot file reference. Boot file is executed, all necessary files are downloaded, and optional we can mount network file server if you want. Matchbox. This is the first piece for Bootstrap. It's open source project from CoreOS. Basically, Matchbox takes care of mapping physical machines based on some labels. It might be MAC address to PXE boot profiles. It runs HTTP and gRPC service. It has iPXE server, which is PXE with some metadata over HTTP. And it provides OS configuration. It can be run as a container, but it requires a host network. For some reason, it doesn't. Docker image doesn't work on ARM architecture, so we had to run as a standalone systemd process instead of Docker container. Matchbox can be configured using files and directory structure. By default, it's varlib matchbox. It can be also configured using Terraform module. So we have groups, profiles, ignition, and assets. Groups are selector for machines based on, like I said before, based on some label. In this example, we have MAC address for this controller node with some metadata and corresponding profile. Profile specify the kernel and initial RAM disk images. We can also pass kernel arguments, even arguments to the bootloader if necessary. And it has reference to ignition config. This directory consists of static assets. Mostly it's for OS images. And ignition consists of a bunch of ignition templates. You can think about that as OS configuration. I will explain what ignition is later on. The next thing is dnsmasq. It's quite a mature project, but it can handle a number of things. It can work as DHCP server. If you already have DHCP server on your network, you can run it in proxy mode. It can be run as it runs DNS, TFTP, and has boot file reference. It can be also run as a container, but it requires network admin. Okay, so let's summarize how does it fit together. Matchbox takes care of PXE network boot, provides network boot endpoints, and takes care of mapping physical machines to PXE profiles. On the other hand, dnsmasq runs DHCP and provides network configuration, and TFTP to transfer data. Everything is running on Raspberry Pi, which is provisioner for other nodes. As an operating system, we will use Container Linux from CoreOS because I like it. It's minimal operating system with basic userland utilities, which means that almost everything custom is running as a container. It runs nearly on any platform, whether physical, private, public, cloud. We run it on production. Another nice thing about CoreOS is the update mechanism, which is quite interesting, and basically it's really secure because let's say that CoreOS is booted off partition A and update will be installed on partition B. So then we can restart CoreOS and it will be booted off partition B. In case of any problem, we will come back to partition A. Ignition is a provisioning utility for Container Linux. It's based on YAML file, which is actually the Go template, which can be rendered with some configuration files. It has a bunch of systemd services, which starts Docker containers. We can provide static files. It can even partition your disk because it's executed during early boot process. In order to understand when and where Ignition is executed, let's take a look at the Linux boot process. So BIOS perform power on self-test, which checks status of physical devices. Then it loads master boot record. Master boot record loads bootloader, and then bootloader loads kernel image and something called initial RAM file system. So this is where Ignition comes from. So as you can see, it's pretty early in the boot process. It's before user space, so we can do many things here. And then kernel loads modules and starts system first process, and then we have systemd services up and running based on some defaults. After we covered all building blocks needed to bootstrap, let's take a look at the Kubernetes node boot process. So obviously we have to power on bare metal machine, receive network configuration from DHCP, and then we can start booting over the network using PXE. We have first OS boot with configuration via Ignition with corresponding profile based on some label. And also we can provide additional assets like TLS certificates used by various Kubernetes components and some of the Kubernetes manifest. Then kubelet systemd service starts and loads Kubernetes manifests. Like I said before, kubelet is a primary node agent. It's focused on running containers, and during the startup it loads Kubernetes manifests specified by pod manifest path. So it will load one by one Kubernetes manifest. But on the other hand, it takes care of configuring container network interface on this node based on CNI confdir parameter with configuration for CNI. Okay, self-registration of nodes. So when kubelet starts, it will attempt to register itself with API server based on bunch of manifests. So we have register node true, which is default. We can set it to false and do it manually if we need to. Also, we can specify additional node labels to distinguish type of the node, whether it is worker or controller or different set of nodes, for example for Bastion. And also we have to pass kubeconfig with location of API server and corresponding certificates to be authorized. And we can specify node status update frequency in seconds, which means how often kubelet will send health checks to API server about status of its node. Once kubelet is up and running, it loads kubeproxy manifest, which takes care of TCP and UDP forwarding. It doesn't understand HTTP because backend is based on IP tables or IPVS rules. It can be specified by proxy mode. In this example, we have IP tables. And another component is the kube API. So it will be loaded in the same way as kubeproxy by kubelet. Basically, it exposes REST service for other components and users. This is the only component which communicates with SHRD cluster. And it has various auth methods. So as you can see, we have a bunch of parameters in order to communicate with SHRD and authorization mode. In this example, we have role-based access control, which is the most fine-grained access control. Okay, we can talk about other components like kube controller, kube DNS, even load balancer, ingress, and storage. But in my opinion, we can safely assume that kubelet, proxy, and kube API are enough to say that we have up and running Kubernetes cluster. So that's pretty much enough to make it work. And this leads us to the cloud. I think that Bootstrap on cloud is not so different than on bare metal. Instead of providing physical machines, we have to use different tools on little bit higher abstraction layer. So we have to decide what cloud provider we would like to use and what provisioning tool, whether it is Ansible, Terraform, or CloudFormation in Terraform, or in terms of AWS Cloud. Also the same stuff like for bare metal, so OS image and OS configuration. This is the example in terms of AWS Cloud, how it might work. Just high-level overview. So we have PKI, which stands for Public Infrastructure, a set of TLS certificates used by various Kubernetes components. And below we have cloud config, which is nothing more than Ignition in our example. So using Golang and Go template language, we can generate and combine it with CloudFormation stack, which will be applied in AWS Cloud. And then we have something called autoscaling group, which will start EC2 instances and provision CoreOS using cloud init. And then we can start applying Kubernetes manifest and create a bunch of pods. If you are interested in this kind of things, you can find more on Virtus Lab blog. So this is pretty much the same what I was talking about today. And this is the next blog post about anti-fragility in Kubernetes. Quite interesting topic. Yeah, so that's pretty much all I have to say today. Obviously, there are more ways how we can bootstrap Kubernetes cluster, but I wanted to give you a high-level overview how it might work and do not overwhelm you with amount of technical details. I hope you like it and see you next time. If you have any questions, I should suggest to have a chat after Pavel talk because we are out of time. Thank you very much.